conference, also the participation of the students and researchers alike. Well, I plan to talk about fuzzy topology, but just yesterday I found out my colleague who introduced these notions didn't know that this notion has been introduced in 2013. So I decided to change the subject to almost continuity with via delta and beta open sets, which I have several papers actually. For example, a paper with Al-Shumrani and Özel and Rayesh, a new type of contract continuity via delta beta open sets, and two special functions in topological spaces, which I and Professor Rayesh, which is a very nice and very good mathematician, Indian mathematician, we initiated this work. So this paper also is joint work with Professor Miguel Caldas from Brazil, Rio de Janeiro University and Sarania, and Professor Rayesh, which we initiated this work and made it to this, which we obtained some results. Okay. Well, the aim of this talk is to introduce and characterize a new class of functions called almost delta beta continuous functions in topological spaces using delta beta open set, which are very useful actually, and it is open for research in digital topology, multifunctions, and so on. But I have, of course, already some papers about this notion and utilize actually delta beta open sets. Okay, why I am not? It is stands as I am not presenting anymore. Why not? It is strange. Because of maybe the connection, I don't know. Can you see the slides? Because
no, sir.
Yes, Professor, the slide is visible to us.
you can see the slides? Okay, that's nice. Okay, no problem. No problem, no problem. We manage. Okay, in 2006, my colleagues Hatir and Nouri, Professor Nouri, have introduced a big form of open sets called delta beta open sets. And we know that generalized open sets actually they found their place in general topology, not only in general topology, also in other parts of mathematics. And they are very useful, important notions in real analysis, and of course the various modified forms of classical notion in general topology, for example, continuity, separation axioms, and so on. They are very useful. I am thinking about manifolds, for example, also in algebraic geometry and so on. It is really vast, you know, the topological properties. Also in fiber spaces, the fiber topology, which one can use actually this modified separation and modified continuity to define the fiber space and so on. So, but in this talk, the main purpose of this talk is to introduce and investigate a new class of functions called almost delta beta continuous function, which is already actually introduced weak delta beta continuous functions, and these two are related to each other. Well, some basic notions. I go very fast through it. I know that those involved in this research, they know, but I know also that maybe some people are sitting there and they're hearing this, that they are not familiar with these notions. So I go through it. So let's say we have a topological space and take a subset of it. So the closure interior, we use the notation CLA and INTA. It's interior of A and closure of A, respectively. And a subset A of a topological space said to be regular open if A is equal to the interior of closure of A. And if we take, for example, a subset A of a topological space, it is delta open if it is the union of regular open sets of the space. Of course, the complement of regular open set is called regular close, and the complement of a delta open set is called delta close. If you take the intersection of all delta closed sets of the topological space containing A, then it is called the delta closure of A, and it is denoted by CL delta A. We use this notation, of course. Then we have some introduction concerning the theta open set, which you have some partial results concerning this. So if you take a point in the space, with the space we mean actually the topological space, it is called theta cluster point of A if the intersection of A and closure of A is different from empty set for any open set of X containing X. And the same is true, theta cluster points are defined this in the same manner, by the same token as it is the definition of cluster points, and but by introducing actually theta open sets. So one can define the theta closure of A and other notions, theta interior and so on. So by utilizing this theta open set and so on, actually I and Professor Callas and Nuri produced a paper called Contra Theta Continuity in Topological Spaces, which is published in Q&A in Japan, the Q&A in topology in Japan. So there are lots of results, new results we found, and one can use it in maybe in this relation. We didn't actually consider it that much. Well, what is delta beta open sets? We know that if you take a subset of a topological space, we say it is delta beta open if it is the subset of the closure of interior of the delta closure of S. And the complement is called delta beta closed set. Of course, if we take the intersection of all delta beta closed sets containing S, then it is called the delta beta closure of S, which we use this notation as you can see it. The same is true with delta beta interior of S, which is defined again with actually exactly like the interior of a set, but using delta beta open sets. I mean, we can use by union of, for example, all delta beta open sets containing in S, then we can have this delta beta interior of S, which is denoted by beta interior of delta S, which you can see it. If you take the set of all delta beta open sets of a topological space, then we denote it by delta beta open of delta beta O of X to make it easier, you know, to make our notation more compact and available. The set of all delta beta open sets of a topological space containing a point X is denoted by this, that we stipulate that a point X is involved. Okay. I know you are tired because here it is 9:50 here in the morning. I think there it is afternoon, and you have there were lots of talks, technical talks and so on. So you are tired, I know that. Just bear with me, please. So if you take a subset B, which is X.
No problem, sir.
Okay, thank you. So
okay.
Usually once it is a technical talk, you know, it is lots of, you know, notation and this sort of thing. So those who are not familiar with these notions should be also involved and to understand what is going on. Yes. So if you take this subset of topological space, it is said to be a delta beta neighborhood of a point if there exists a delta beta open set U such that X belonging to U and is subset of P of X. Actually, it is the same notion in general topology, but modified notion are used, and we are we give some surprising result actually, and deepen those results we have, classical results we have in general topology, and give us a more deeper insights about separation axioms, continuity, and so on. Okay, we have a function between two topological spaces, and those are introduced, of course, and delta beta continues. And if we have a point, for example, in a topological space, and for every open subset of the range containing FAX, then there exists a delta beta open set U containing X such that FAU is a subset of. If this property satisfied for at each point of X, then we can see that this is delta beta continuous. So, okay, this is separation axioms defined by delta beta open sets. And we have T1, T2, and one can also define, I think we have defined T0, and also some other weaker separation axioms like D0 and D1 and D2. Of course, there are lots of them. One can actually decide to do research. Also, the fuzzy aspect of it also very important, actually. Well, this is the notion is defined exactly the same as T1 by involving delta beta open set. The same is T2, the same, using delta beta open set. So we take the definition, which is the main part of the paper, which is called almost delta beta continuous. The definition is the same, exactly like almost continuous functions, but by using delta beta open set means that at a point X belonging to the space, the function is delta beta continuous if for each open subset V of Y containing FAX, one can find a delta beta open set containing X such that FAU is a subset of interior closure of V. And if it is this property satisfied with at each point of X, then we say that it is almost delta beta continuous. So the remark is that almost beta continuity implies weak delta beta continuity. It is obvious. The same is true with almost continuity, which implies weak continuity. And it is obvious that almost delta beta continuity implies by delta beta continuity, which I have a paper about it. I have a paper with Ashumrani and Uzel and Professor Raish about a new type of contract continuity via delta beta open sets. So we have made lots of paper actually initiated by Professor Raish, which is a magnificent, very fantastic, with fantastic results. And we made some papers in this field. We can see at the consensus of the implication not true in general, and we have some examples to prove it. So the examples are here, very simple examples. One can see which we have a space of 3 points and a topological space. And then we have another topological space, which is containing of theta and single point and so on. Define functions. Then we say that if FA is equal to B and FAB equal to C and FSC equal to A, then F is almost delta beta continuous, but not delta beta continuous. It needs something, this delta. I can see it, yes. If we take, for example 3-4, we have a topological space, then we have, as you can see it, A, B, C, and it consists of empty set and the singleton A and B, and A of B and X. Then we have a function which is defined by FA is equal to C and FAB equal to A, FSC equal to B is weakly delta beta continuous, but not almost delta beta continuous. This is a result concerning almost delta beta continuous functions, which the following statements are equivalent. It means that once you have a almost delta beta continuous function at a point x, then for each neighborhood of f(x), which x belonging to the closure of interior of the delta closure of the inverse of semi-closure of v, for every open set v of y. And the same is true with the inverse of v's subset of the beta interior of the delta of the inverse of semi-closure of v for every open set v of y. So the proof is here. It is actually a simple proof. It is standard proof, which you can also, you have seen it in maybe also other papers. So it is not a new one, and this proof is, in my opinion, very easy to complete. If we take this function, then we can say that also these statements are equivalent concerning the almost delta beta continuous functions when you have a regular open set, regular closed sets, delta closure of v, and delta open set of y. So you have all these statements are equivalent, which one can use it to prove several terms and results. So the proof is here. So I don't go through it. If somebody wants to have this proof, then they can get the paper. So also it is a standard proof. It is not so difficult to prove such terms. We take this one for a function. The following statements are equivalent. As you can see, that these also standard results by using the notion we introduced. But it is nice actually. If you had some other type of almost continuity, also you can see that some of these results are the same. But when you use them, for example, in multifunctions or other part of mathematics, for example, in digital topology and so on, you can see the differences when you apply them to other parts, also in fuzzy or nitrosophic theory and so on. This is the proof of theorems we have. Also here, the rest of the proof, which, as I mentioned before, it is actually the same as those for almost continuity and so on. Well, we have this result. Let's take two subsets of topological space. If A belongs to delta beta open set of X, and the B is delta open in the topological space, then we can see that the intersection is belonging to delta beta open set of B. If you take a function which is delta beta continuous, and those who don't know, actually, I have also introduced faintly delta almost continuous functions with Professor Nouri and Keldas and Rayesh in 2009, which is published in Academy of Sinica in that time. So they can see some results there if they can find the paper. Also in faint, also in a new type of contract continuity via delta beta open set, we have some results. If one wants to actually expand these results by using these papers, then you can do it. Actually, this is an open research area. Okay, if you have a function between two topological spaces, which is delta beta continuous, and A is a delta open set of the topological space, then the restriction of A to A is delta beta continuous. And it follows from the above lemma. So then we have a delta open cover, which is exactly as the notion of cover. And by utilizing delta open sets, as you can see it, we take the collection. We say that it is a delta open cover of the subset A of a topological space if A is the subset of union of G lambda, which is an index belonging to a big lambda, and we take the complement of G lambda, which belonging to delta open sets of X. Then we have these results as a consequence. If we take a function, then we have also a collection which is ui, and the little I is belonging to the big I, be a cover of X such that this guy ui belonging to delta open set of X, then the restriction to ui is delta beta continuous for each I belonging to I. So if it is true, then we can conclude that F is delta beta continuous. The proof is not so difficult. I go through it. Let's take any open set you can find, for example, in the range of the function. Then the restriction is delta beta continuous for each I belonging to the big I. It follows from this that there is the inverse of the restriction. The inverse of the restriction of V is delta beta open set in UI. So we have the result that the relation that we have the inverse of this open set is equal to the union of V intersection or the intersection of UI and the inverse of V is equal to union of the inverse of restriction of UI F to UI of the V. So by lemma 3.8, we can see that the inverse of V actually the beta open set, and this means that F is delta beta continuous. So it is not a difficult proof. But another notion which one can use, delta beta convergence and so on, but one can also define US convergence. So if you go to in research gate, you can see a paper or two. This is also open. One can produce it, produce a new joint a paper if it's possible, which one can use US spaces. Actually, also some special type of convergence theorems one can obtain. So if you take a filter base, then we say that delta beta convergent at a point X belonging to X if for any U belonging to delta beta open set of X containing X. So there exists a set B belonging to lambda, big lambda, such that B is a subset of U. So a filter base big lambda is said to be R convergent to a point X in X if for any regular open set U of X containing X, there exists B belonging to the big lambda such that B is a subset of U. Okay. Lots of results. Bear with me. You are tired. I hope that you have your cup of coffee beside you and you drink it, or tea. The Indian tea is very nice and good, tasty. Yes. Where I have been. Yes, this result is also obvious, so I don't go through the proof. A first-year student in general topology can prove this, or maybe a good student from the high school. Well, if a function is delta beta continuous, then for each point X belonging to X and each filter base in X, delta beta converging to X, the filter base is converging to Fx. The main issue is that as it is simple, but when you have formulated in these new notions, then you can see there are vast application of it. So it is this which is very important. Then we take a sequence. It is said to be delta beta convergent to a point X if for every delta beta open set of V of X containing X, there exists an index XNOR such that if we take, for example, all n which is bigger than or equal to n0, then xn belonging to V. If we take a function which is almost delta beta continuous, then for each point X belonging to X and each net which is delta beta convergent to X, then the net is convergent to Fx. So here, oh my God, yes. If we take, for example, an injective function, which is also almost delta beta continuous, and y is RT1, it is regular open sets are involved. A T1, as usual in general topology, by involving regular open sets, then the topological space is delta beta T1. It means by involving delta beta open sets. So if we take a RT1, then the range is, if we take the range as RT1, then for any distinct points X and Y in X, there exists regular open sets V and W such that Fx belonging to V and Fy is not belonging to V and Fx belonging to W and that is not belonging to W and Fy belonging to W. Since F is delta beta continuous, the inverse of both V and W are delta open subsets of the space, topological space, such that X belonging to the inverse of V, Y is not belonging to the inverse of V, X is not belong to inverse of W, and Y is belong to inverse of W. And this shows that the topological space is delta beta T1. So we have another results. If we have an almost, here should be an almost, not the A, but let me make it, should be an. Okay, an almost delta beta continuous injective function, and the range space is a RT2, then we can see that X, the topological space is delta beta T1, so T2. So the proof is not so difficult. We go to the next notion. We have a function is said to be faintly delta beta continuous if for each X belonging to X and each theta open set V of Y containing Fx there exists U. It means a delta beta open set of X containing a point X in X such that Fu is a subset of V. Okay. The implication holds for the following properties of a function. So we have what type of functions are involved: delta beta continuity, almost delta beta continuity, weakly delta beta continuity, and faintly delta beta continuity. So if in addition Y is regular, then the 5 properties are equivalent of one another. So very interesting, actually. A function is said to be delta beta pre-open if U belonging to pre-open sets of U and Y for every delta beta open set U of X. A function is called a delta beta pre-open and weakly delta beta continuous. If it is so, so F is almost delta beta continuous. Yes, and so one can also make the composition of it. So it is the proof. an easy proof. We take a point in the topological space X, and we take also an open set of Y containing f(x). Since f is weakly delta beta continuous, then we can find a delta beta open set U of X containing the point X, such that f(u) is belonging to closure of V, which is weakly delta beta continuous. Since f is delta beta P open, so we take FEU, which is a subset of interior closure of FU, and at the same time it is the subset of interior closure of V, and hence F is almost delta beta continuous. So the proof is not so difficult. So we have some other notions. A function is said to be R map if we take in V is regular open X for every open set V of X. And the function is delta beta irresolute if the inverse of V is delta beta open in X for every delta beta open subset of Y, V of I. So we have, again, which is also a simple proof. One can use the composition of two functions. We have, if you take these two functions, then the composition is if f and g satisfy one of the following condition. Either it should be, for example, almost delta beta continuous and g is R map, or f is delta beta irresolute and g is almost delta beta continuous, or f is delta beta continuous and g is almost continuous. So it is a nice result, actually. The other notion is almost regularity notion in general topology, and the semi-regularity, which is well known to topologists. So topological space is almost regular if for any regular closed set of X and any point is belonging to the complement of F, there exists disjoint open set U of U and V such that X belonging to U and F is a subset of V. So the topological space is semi-regular if for any open set U of X and each belonging to U, X belonging to U, there exists a regular open set V of X such that X belonging to V and V is a subset of U. So we have these results. So I don't go through the proofs since they are easy proofs. I just mention the results. If a function is weakly delta beta continuous function, Y is almost regular, then F is almost delta beta continuous. If a function is the next result, if a function is an almost delta beta continuous function and Y is semi-regular, then F is delta beta continuous. We have a definition. Delta beta frontier of a subset of the topological space, which is exactly the same as what we have in general topology by involving delta beta open sets and delta beta closure of A and the complement of A. So this notion also useful in the next theorem, which I read now. The set of all points X belonging to X in which a function is not almost delta beta continuous is identical with the union of delta beta frontier of inverse images of regular open set containing fx. So the proof are also interesting, but I don't go through it now. There is a lemma which is proved in reference 4, and the product of two delta beta open sets is delta open. So another result says that if we have a function f1 from x1 tau to y and sigma is weakly delta beta continuous, and we have another function which is go to from another topological space as a domain x2 and tau to y and sigma, we say that it is almost delta continuous, and so if F1 is weakly delta beta continuous and F2 is almost delta beta continuous, and the range of space Hausdorff, then the set of if you take the order points x1, x2 in the product of x1 and x2, then f1 x1 is equal to f2 x2. Then this set actually is delta beta closed in the product space, and it is also a well-known result. But of course, this should be adjust with respect to almost delta beta continuity. I hope that I have more time. Do you have time, or I talk too much maybe? If for each pair of distinct points, x1 and x2 in a topological space, there exists a function of x into a Hausdorff space y, such that fx1 and fx2 are different, f is weakly delta beta continuous, and f is almost delta beta continuous at x2, then x is delta beta t2. So the result also is not so. It is interesting actually, but I don't go through it now. Another definition, just which result we obtained, and the new notions actually. Okay, the graph g of f of a function is said to be delta beta closed if each point, let's see, x and y, belonging to the product space at the complement of course, g of f, there exists u, means a delta beta open set containing x, and open set v of y containing y, such that the product space of u and v, it means that if you take the product of u and v and intersect with g of f, then this intersection is empty. Another lemma says that if you take a graph of a function which is delta beta closed in the product space, then we say that this graph is delta beta closed if and only if for each point belonging to the complement of GF taking the product space x multiply y, then there exists a delta beta open set of x u containing the point x, and an open set v of y containing y, such that the intersection of FAU and v is empty. And this is exactly as a direct consequence of definition, the definition 332. This definition. The definition of the graph of the function, which is say delta beta closed. Okay, another results concerns in the graph. If you have a function which is delta beta continuous almost, and y is Hausdorff space, then the graph of f is delta beta closed in the product space. This x multiply y. And also the proof is that is such that if let us see that the point is not belonging to the graph, and this means that y is not the same as fx. Since y is Hausdorff, then there exist two open sets, v1 and v2 of y containing fx and y respectively, and take intersection, and such that this intersection of course is empty. Since f is almost delta beta continuous, then so from the definition there exists a delta beta open set u of x containing the point x, such that FU is belonging to interior of the closure of V1, and consequently the intersection of FAU and V2 is empty. This shows that the graph is delta beta closed in the product state. So we have the notion of delta beta compact, exactly as a compact space by introducing delta beta open sets. But finding the example was very difficult. So I'm thinking about the example for this type of compactness. Sometimes it's not that easy to find them. Then we have the notion of nearly compact spaces if every regular open cover of X has a finite subcover. So then we have this result, which related to almost delta beta continuous functions. If it is this type of functions, we have it is surjective, and the domain is delta beta compact, and the range is nearly compact, and then the proof is standard. But of course, it is a new proof, new results. If we take a function which has the delta beta closed graph, then if a co, which co is any subset which is delta beta compact relative to X, it is closed in Y. So this is the proof. And to prove this, we take a point which is not belonging to FACO, then we take a when Y is not belonging to it, so it shows that the point X and Y does not belong to the graph of F for each X belonging to Co. And since the graph is delta beta closed, so one can find a delta beta open set UX of X containing X, and also an open set VX of Y containing Y, such that the section is empty. Then we use the lemma which we mentioned before. So the family we have UX with X belonging to the cover of Y by delta beta open set. Since Co is delta beta compact to X, one can find the finite subset Co0 of Co, such that Co is belonging to union of this collection. It means UX which X belonging to Co0. If we set V to the intersection of the collection of VX with X belonging to Co0, then V is an open set in Y containing Y, in Y big containing the point Y. Therefore, we have the intersection of Co and V, which is a subset of the union of UX. Union goes through for actually all the points X belonging to Co0, intersection with V, which is also a subset of the intersection of FAUX and V, which the union goes through all points belonging to Co0. This intersection, this is empty. It follows that Y doesn't belong to the closure of FACO, and therefore FACO is closed in Y. So it was also a standard proof. So we have used these references. As you can see, used much more the results of reference 4. And also you can see that this 5 on Feintel delta beta continuous function, which is published in Bulletin of Institute of Math, Academy of Sinica, okay, in 2009. So these references we have used. Thank you very much for bearing with me to hear this technical talk. I have you enjoyed, and I have inspired you, because there are lots of notions defined which should be specified, and also in connection with contra delta beta continuous functions and so many other notions, also in multifunction theory, quasi theory, neutrophic theory, and so on. So also separation axioms. Lots of other weaker separation axioms, like, for example, delta beta are 0, for example, delta beta are 1, and so on. Thank you very much. Thank you very much for the organizing committee and everybody who made this conference possible. Thank you very much for inviting me. Thank you very much to the participants. Thank you.
Participants, if you have any queries, you can now proceed. Please post your queries in the chat section. Thank you, sir, for giving your valuable insights.
Thank you very much. Thank you very much for inviting me. Thank you.
For the next session, I call upon Dr. M. Vivek Prabhu, sir, Assistant Professor, PG and Research Department of Mathematics, Konganadu Arts and Science College, to introduce the speaker. Sir, please.
Thank you. It gives me immense pleasure to introduce our honorable speaker, Dr. Alexander Picassini, sir. He has completed his degree in mathematics from the University of Milan in the year 2005. His area of research is in the field of differential geometry, especially in Riemann geometry. Currently, he is collaboratingly working with Professor Syed Jafari, sir, in Mathematical and Physical Science Foundation. So we are very much privileged and honored to have you here with us, sir. It's my immense pleasure to invite Dr. Alexander Picassini, sir, to deliver his speech on the topic on Pndp manifolds. So on behalf of the management and department, I wholeheartedly welcome you, sir. Now I hand over the session to you, sir, please.
Okay. Can you hear me?
Yes, sir. Yes, I can hear you.
Can you hear me?
Yes, sir. You are audible.
Okay. Thank you so much for the invitation. Okay. For me, it's a great honor to participate today. I think I thank all the organizers and the Kongonadu Art and Science College for this opportunity, and also the Mathematical and Physical Science Foundation. Today I would like to talk to you about the Pndp manifolds, a special type of Einstein Bartlett product manifold, which were introduced by me, Professor Said Jafari, Professor Jenab Ozel, and Professor Patrick Linker. Okay, we can start. Wait a moment, please. Okay. Okay. Can you see my desk?
Sir.
Okay, thank you.
So we can see your presentation.
Yes, sir, it will do.
Okay. We provide a possible way of construction, a new kind of manifold, which we call partially negative dimensional product manifold, and Pndp manifold for short. In particular, a Pndp manifold is an Einstein Bartlett product manifold of a special kind, where the base manifold B is a Riemannian or a pseudo-Riemannian product. We can see the Riemannian product B is equal to Riemannian product from E equal 1 to Q first of Bi manifold product with another Riemannian product from
I equal to Q first plus 1 to Q tilde. This formula, the second product, is an Einstein manifold. So we can consider the B manifold as a product manifold, B equal B first product with B tilde, where B tilde is an Einstein manifold. Okay. We will hit an Einstein product manifold, and we will introduce also the concept of negative dimension. As a mathematical tool for fiber manifold F, we will use the derived geometry. And about this, we recall that if A and B are two transversal submanifold of codimension A and B respectively of a manifold M, then their intersection that we call C is again a submanifold of M of codimension A plus B. The derived geometry explains how to remove the transversality condition and make sense out of a non-transversality intersection C as a derived smooth manifold of codimension A plus B. And in particular, if our submanifold C, its dimension is equal to dimension of M, the manifold, subtracted A subtracted B. And in this case, the dimension of C can be negative. Okay, the obtained dimension, for obvious reason, are not related to the usual geometric concept of dimension. It's a virtual dimension, and this aspect gives the possibility to study the Pndp manifold as well as from the differential geometric point of view, and also with the correct interpretation from the speculative and applicative point of view. Okay, allora, well, this is the classical definition for Einstein-Varpert product manifold. And definition 1. A Varpert product manifold, M, and with the G bar, I mean the metric of the Varpert product manifold, is equal B, the base manifold, and G, its metric. Varpert product, where F is the Varpert function, with the fiber manifold F and its metric G double dot. Okay, and the metric G bar of a Varpert product manifold is equal to G, that is the metric of the base manifold, plus the Varpert product squared multiplied by G double dot. And this is Einstein if and only if the system 1 is satisfied. So the Rick bar, I mean the Ricci curvature of the manifold M, is equal to lambda multiplied by G bar. And so with the Rick, I mean Ricci curvature of the base manifold, subtracted D divide F, where D is the dimension of the fiber manifold, F is the Varpert function, multiplied by the Hessian of F referred to the base manifold equal lambda multiplied G. With the Ricci double dot, I mean the Ricci curvature of the fiber manifold, and is equal mu multiply G double dot. And in the end, we have F multiply, F is the warped function, multiplied by the Laplacian of F, always referred to B manifold, plus D, the dimension of the fiber manifold, subtracted 1 multiplied by the absolute value squared of gradient of F plus lambda multiply squared F equal to mu. Okay, lambda and mu are the constant. And the important thing is that the warped function F is defined on the base manifold B with value to R positive. With R positive, I mean the set of real numbers. So the warped function is a smooth positive function. Okay. The second one is the definition of the Pndp manifold. Okay, we call the Pndp manifold a warped product manifold, as we said in the previous definition, that satisfy the system 1. Okay, this system 1, but it must satisfy it considering same new condition. For example, the base manifold B is a Riemannian or pseudo-Riemannian product manifold. So we B is equal to B1 times B2 times B3, etc. With G of B manifold, that is the product manifold, is the sum of each metric. Okay, and we can write B as B equal B first product B tilde, where B tilde is an Einstein manifold. Okay, so we have Ricci tilde is the Ricci curvature of B tilde, the manifold B tilde, the submanifold, equal to lambda multiplied G tilde, where this is important. Lambda is the same constant, same value for the system 1. Okay. Well, okay, with the dimension B tilde equal to N tilde, everything referring to B tilde as marked with tilde. So the dimension of B tilde is equal to N tilde. And B first is the Riemannian product from I equal 1 to Q first of B1 manifold with dimension B first equal N first. So the dimension of B is equal N, and it is equal N first plus N tilde. The warping function F is defined on B with value on R positive, and it is F of X and Y equal to F first of X plus F tilde of Y, where each is a function on its individual manifold. That is, the F first function is defined on B first with value to R positive, and F tilde is defined only on B tilde manifold with value R plus, R positive. And F can also be a constant function, okay? The fiber manifold F with its metric G double dot is a derived differential Riemannian flat manifold with negative integer dimension M, where with the derived differential manifold we consider the derived manifold as a smooth Riemannian flat manifold by adding a vector bundle of abstraction. In particular, we consider for F only the space forms RD. With RD, I mean the d-dimensional real set with orthogonal Cartesian coordinate such that its metric G double dot is equal to minus Kroneker's delta, okay, by adding a vector bundle of obstruction. So with A, we mean the bundle of obstruction on E. R equal R plus bundle of obstruction E with dimension M equal D, so the dimension of RD, subtracted the rank of E, where rank of E is greater than D. Okay. We consider F such that its dimension is M equal minus D. Since F is equal RD plus E, and on E, that is the obstruction bundle, the Riemannian geometry doesn't work. So we consider and define that every operation on Riemannian geometry done and defined on the underlying RD, okay, and it is considered done and defined on F. For example, if we calculate the Ricci curvature on RD, which is obviously 0, then we will say that the Ricci curvature of F is 0. This because it will be the definition of Ricci curvature for F. Okay. Moreover, if you want the quantity n subtracted d greater than 0, then we must set n first equal to d or equal to minus m. And the special case where n subtracted d greater than 0 would also be first an Einstein manifold with the same Einstein lambda, then B first equal B tilde. Okay. Therefore, to fix the ideas, being as we said that F is equal RD plus E, and on E the Riemannian geometry doesn't work. Every Riemannian geometry operation that we want to perform on F, we perform it on the underlying RD, and by definition it is considered as if it were performed on F. Okay, now I want to underline an important aspect, important not one, I recall. So, since the usual Riemannian geometry works for the underlying Riemannian manifold as for ordinary manifold, we can therefore consider ourselves to able to work with the pseudo-Riemannian geometry on our derived fiber manifold F, defining all Riemannian geometry operation on RD, the underlying manifold, as Riemannian geometry operation made on F, paying attention only to the dimension. In particular, as mentioned above, we work on F by actually working on the underlying RD, in the sense that the since F is equal RD plus E, the obstruction bundle, the calculation result obtained on RD are considered to be obtained and defined on F by taking into account that F has negative dimension. In fact, on the obstruction bundle, we cannot put the metric. Then we do not work on the obstruction bundle with the Riemannian geometry, but it gives negative dimension of F, or virtual negative dimension. Obviously, for what has been said, the tangent space and the vector fields are those of RD, and the scalar product with two arbitrary vector fields is defined as minus Kronecker delta multiplied by VE and WJ. Okay. Okay, we want to underline that the analysis does not differ from the usual analysis from Einstein-Barber product manifold, and the Riemannian curvature tensor and the Ricci curvature tensor of the product Riemannian manifold can be written respectively as the sum of Riemannian curvature tensor and the Ricci curvature tensor of each Riemannian manifold. This could be also a special kind of Einstein sequential Barber product manifold. And the Barber product between M1 and M2, where H is the Barber function, and there is another Barber product where H bar is the Barber function with M3. In our case, in the Pndp manifold case, we have H equal 1, and M2, the manifold M2, is an Einstein manifold, okay? And the manifold M3 is a derived smooth manifold with negative virtual dimension. Okay, let's say we have the proposition. If we write the B product in our base manifold as B equal B first product B tilde, where, okay, with Ric first, I mean the Ricci tensor of the manifold B first. Ric tilde is the Ricci tensor of the B tilde manifold. G first is the metric tensor referred to B first manifold. G tilde is the metric tensor referred to the manifold B tilde. And F is equal F first plus F tilde, the smooth warping function. I recall that F is defined on B with value in R positive, where F first is defined only on B first, is a smooth positive function with value in R positive, and F tilde is defined only on the manifold B tilde with value R positive. Okay, we have that the Hessian is the squared nabla F is the Hessian of the Barber function F is equal to tau first with star is the pullback of the Hessian first of F first. So we do the pullback on the manifold B first, plus tau tilde with star is the pullback for the Hessian tilde for the f tilde function. So we do the pullback on the B tilde manifold. Okay, is the okay? I write Hessian referred or its individual metric. We have that signs B tilde is Einstein. We have that the pullback of Hessian referred to B tilde is equal to 0. The gradient of f is referred on its individual metric. So the absolute value squared of gradient of f is equal the absolute squared value squared of f first, the gradient of f first, plus the absolute value squared of the gradient referred to f tilde. And delta f is the Laplacian of f is equal Laplacian first of f first plus Laplacian tilde of f tilde. But since the Hessian referred to f tilde is equal to 0, then the Laplacian tilde f tilde is equal to 0. Okay, so the Ricci curvature tensor will be okay. Here below is the system in which we have shown the Ricci curvature tensor referred to the various vector fields for such constructed manifold. That is a warped product manifold in which B, the base manifold, is equal B first product with B tilde. F is a Riemannian flat manifold, and the warped function f is defined as f of x y equal to f first of x plus f y, where f first and f tilde are defined on B first and B tilde respectively. Okay, we have the system 1 with 4 star. Okay, and this is the Ricci curvature tensor for the various vector fields. Okay, then we have come to the formal definition of a Pndp manifold. That is, here are the system that allow you to build a Pndp manifold, which are nothing more than the system 1. Okay, so the system 1 is this. Okay. Okay. That we saw in the definition in 1, okay, but adapted to the new structure of the Pndp manifold. Okay, allora, theorem, a warped product manifold, we derive differential fiber manifold F equal Rd plus E, where E, I recall that is the abstraction bundle, and dimension of F, a negative integer, is a Pndp manifold as defined in definition 2. If and only if, okay, here we basically apply the Einstein condition to the system 1 with 4 star, okay? We apply the Einstein condition and we obtained, and then we got the new system 1 with the 3 star. since the RIC is the Ricci curvature of B, and B is a product between B first and B tilde, then RIC is equal RIC first plus RIC tilde, and is equal lambda multiplied by G first plus G tilde, etc., etc. Okay. Now we have two systems. The first for n subtracted d equal to 0, and n subtracted d less than 0. Okay. I recall that n is the dimension of Pndp manifold, and d is the dimension of the underlying manifold of FRD. If n subtracted d is equal to 0 or n subtracted d is less than 0, we used the system 1 with 2 star. Okay. And here the system 1 with 2 star, basically it is the system 1 with 3 star, in which we have made the contraction to the first 3 equations. We have R first instead of RIC first, and we have Laplacian first instead of the Hessian first. We have we've made basically it is the same system in which we have made the contraction. Okay. While if n subtracted d is greater than 0, we have another system, the system 1 with 1 star. Okay, and the proof, we apply the condition that the vapor product is Einstein, and we with this condition we obtained this 3 system. Okay, recapitulating, we use the derived geometry to define the fiber manifold, which explain how to remove the transversality conditions and make sense of a non-transversal intersection, and therefore admit the presence of negative dimension. It is the virtual negative dimension. Since we consider the fiber manifold F as RD, adding a vector bundle of obstruction, then we work with the Riemannian geometry on F, working only on the underlying RD, such that all the Riemannian geometry operation made on RD are considered as defined on F. Then the classical construction for the vapor product is the same. We consider the vertical vector fields, for example, U and V, as lift of the vector fields of F. The development of the formula remain the same. Okay. If X and Y are the lift from B, they are horizontal and so constant on the fibers. So substantial remain the same. Okay. We obtained an Einstein vapor product manifold, M with the G bar, the metric, because from the geometric point of view, the fiber is RD, but taking into account that the manifold obtained as the fiber manifold with negative dimension. Okay. In this formula, I use RD instead of F. We can see here M, the Pndp manifold, M with the G bar metric is equal to the varped product with F, the varped function, between B, the product manifold, okay, where B is equal to product between B first and B tilde, and B tilde is an Einstein manifold. Only B tilde is an Einstein manifold, and I wrote RD with G double dot. Okay. But this taking into account that the manifold obtained as the fiber manifold with negative dimension, because we use the bundle of obstruction, and the dimension of F is given by D subtracted rank of E, and this could be negative. So the outcome manifold, our Pndp manifold, is N plus D subtracted rank A dimensional manifold. Okay. Another important observation is that we consider RD because in the space form, because from a speculative point of view, which we'll consider shortly, the negative dimensional space is used only to make the Pndp manifold dimension virtual smaller than the base manifold dimension. Therefore, for this purpose, we consider it in the simple possible form. But we can also consider any manifold with a flat connection. Okay. Well, the Pndp metric referring to a Pndp manifold with negative dimensional fiber, and for not confusing its metric with a metric of a classic Einstein varped product manifold, we denote the Riemannian or pseudo-Riemannian metric of the fiber manifold with the following notation to indicate that F has negative dimension. Okay, so we have a G bar. A G bar is the metric for a Pndp manifold, equal to G subtracted squared F, where F is the varping function, and we have the metric. We have the metric of the RD, so the flat metric. But we put as a subscript the negative dimension F, M in bracket. Okay. So with this notation, we understand that the Einstein varped product manifold is a Pndp manifold because we have indicated the negative virtual dimension M of the fiber. Okay. And then the general metric form of a Pndp manifold is okay, this that I wrote here, where I specify the sum with the G first and G tilde. Okay, below trivial example, the manifold in where the B first and the B tilde are the same and are product between R, the set of real. We have a obstruction bundle E with the rank equal to 4. So we have 4 subtracted 2 Pndp manifold. Okay, that is a Ricci flat. So in this case, in the trivial example, our Pndp manifold have a virtual dimension equal to 2. To satisfy the system 1 with 1 star, we have the constant f equal 1, for example, where f first and f tilde are both constant, and then we have n plus m that is equal to n subtracted d equal to 4 subtracted 2, so we obtain 2 greater than 0, and 2 is the virtual dimension of Pndp manifold. Okay, for its metric is the flat metric, and we have indicated at subscript -2 in the bracket, and with our notation to indicate that it is a Pndp manifold. Okay. Okay. Second part, possible speculative interpretation of the types of the Pndp manifold. Premise. Okay, we assume that the negative quantities exist in nature, and here we consider the possible existence of virtual negative spatial dimension. That is, for some region of an intrinsic nature, or for some initial situation, some of this dimension behave in a way that we can mathematically describe them as virtual negative, which implies, from our speculative point of view, that they interact with other dimension. However, the fact remains that the Pndp manifold could be used to describe anything in nature that has to do with negative quantities. Okay. From the speculative point of view, in this session, we consider 3 kinds of Pndp manifold. The first type, the n minus n Pndp manifold, that has overall 0 dimension. The dimension of the Pndp manifold, dimension of M, is equal dimension B plus dimension F. Dimension B is n, and dimension F is M, and in this case it is equal minus n, so 0 dimension. The speculative result may be interpreted as an invisible manifold, but made up of 2 manifolds with n and minus n dimension, respectively. Then we try to consider it as a kind of a point-like manifold. Okay, 0 dimension, but with hidden dimension. We have the type 2, the n and the minus d Pndp manifold, where n is the base manifold dimension, that is different from d, with d a positive integer number. And the fiber manifold dimension is, I recall, is m equal minus d, so m is a negative integer number. Such that the dimension of M, so the dimension of our Pndp manifold, is equal to n plus minus d greater than 0. And the particular speculative feature of this manifold is that it appears as another Einstein manifold with n plus minus d dimension. The type 3 is like the type 2, but dimension is equal n plus minus d is less than 0 and not and not greater than 0, like a type 2. It is the speculative filtering. For this type, through our special projection, it will be considered as the suspension of a point. Okay, the virtual dimension are not related to the usual concept of dimension in Riemannian geometry. Therefore, our interpretation try, through the product, to consider that the virtual negative dimension of the fiber manifold hide the positive dimension of the base manifold, making the Pndp manifold appear as a desuspension, had been performed. In practice, the derived manifold F has negative virtual dimension, which are far from the usual concept of dimension used in geometry. Being that with the warped product, we have to consider both the dimension of F, virtual, and the dimension of B, which is a Riemannian or pseudo-Riemannian manifold. B is a Riemannian manifold, and therefore the dimension of B is in perfect relation with the usual concept of dimension. The obtained virtual dimension of our Pndp manifold is equivalent to the dimension of the base manifold B with the dimension of the underlying manifold Rd subtracted, and we obtain that the result will be smaller than the dimension of B. From the speculative point of view, we want to consider that the dimension obtained for the Pndp manifold by interpreting that when the dimension of B, the base manifold, come into contact with the dimension of the fiber F, the latter interact hiding the dimension of B. This means that the Pndp manifold will usually visually appear as if some sort of a desuspension has been performed on B. Thus with a hidden extra dimension that we cannot see. Definition 3. Okay, allora, in general, given an n-dimensional space X, the suspension sigma X has dimension n+1. Okay, thus the operation of suspension creates a way of moving up in the dimension. The inverse operation, sigma -1, is called desuspension. Therefore, given an n-dimensional space X, the desuspension of X has dimension n subtracted 1. As we have mentioned in some previous slides, we try to consider the relation between the dimension of the Pndp manifold and the usual geometric concept of dimension as a desuspension interpreted by our spatial projection. For this reason, since each negative dimension can act equally on each positive dimension, so as not to be faced with the choice of which projection of B to consider, we must orient the result of the projection to what reflects certain characteristic. And to do this, we have in our favor the fact that B, our base manifold, that I recalled is equal to B first times B tilde, because B is a product manifold, where B tilde is an Einstein manifold. Okay. And the metric of B is equal the metric of B first plus the metric of B tilde, such that B tilde is an Einstein manifold with the same dimension and the same lambda constant of the Pndp manifold. And therefore, B tilde will be the result of the projection we are going to consider when the dimension of the Pndp manifold, n plus minus d, will be greater than 0. Then the solutions to build the Pndp manifold will be provided by the system 1 star. When the dimension of the Pndp manifold is equal to 0, the solution will be provided by the system 1 with 2 star, and the result will be a dimensionless manifold, zero-dimension manifold. So our projection will provide to a point-like manifold. While when the dimension of our Pndp manifold is less than 0, also in this case, the solution to build the Pndp manifold will be provided by the system 1 with 2 star, and the result of the projection will be equivalent to the desuspension of a point. Okay. Now we have the suspension as a special projection. Okay. If the dimension of our Pndp manifold is greater than 0, that is a system solution, system 1 with 1 star, we have the projection to B tilde. Okay, so our Pndp manifold is considered as B tilde. If virtual dimension of Pndp manifold is equal to 0, we have the projection to a point-like manifold, 0 dimension. And in the last case, if the dimension of our Pndp manifold is less than 0, so system solution is in 1 with 2 star, we have the projection in the suspension of a point. For example, if the dimension of Pndp manifold is equal -4, our projection will project M into an object which will be given by a false the suspension of a point. Okay, here a trivial example of our spatial projection. For example, if we have a Pndp manifold with 3 positive virtual dimension, here we have 6 subtracted 3 Pndp manifold with the f Barclay function non-constant, for example. Since the dimension is positive, we must set dimension B first equal dimension of F, as in definition of definition 2 of Pndp manifold, and this set is present also in the theorem, where we have shown the two system 1 with 2 star and system 1 with 1 star. So our Pndp manifold is such that B tilde 4, product B tilde 5, product B tilde 6 will be an Einstein manifold. And by our special projection, our Pndp manifold with 3 virtual dimensions will be the Einstein manifold B tilde times B 5 tilde times B 6 tilde. Okay. This is only a trial example. Okay, here a representation of a Pndp manifold. We have a B manifold, is a tesseract, a 4-dimensional tesseract. F manifold is a manifold with 2 negative virtual dimension. Here is represented the interaction between positive and negative virtual dimension in our speculative interpretation. So our projection will be R2, because the dimension of the B manifold is equal to 4, is a 4-dimensional tesseract, subtracted the 2 negative virtual dimension of the F manifold. So by our projection, the result will be R2. Okay. We have reached the final part of the part 3, some possible speculative application in financial market and in cosmology. Okay, among the possible application we are working on, one of them concerns the financial market. In this project, I'm working jointly with the Professor Richard Pincock, the Professor Said Jafari, the Professor Jenna Ozel, and the Professor Ozgi Korkmaz, where a Pndp manifold can be used to describe the behavior of the financial market influenced by a ghost field called the dark volatility. This volatility is not fixed in any relevant economic parameter. It is a sort of a negative dimension that greatly influences the behavior of the real market. With our approach, we can describe the financial market as a Pndp manifold in which the fiber manifold corresponds to the dark volatility, and the influence that the latter exerts determines the market structure as an emerging manifold through our special projection. Here, a speculative vision of a Pndp manifold with a virtual positive dimension. We have B tilde is our projection, okay? The emerging financial market from a speculative point of view, through our special projection, the Pndp manifold appear as a B tilde manifold. That is the financial market that emerged due to the influence of the dark volatility. So the rest of the Pndp manifold, which represent the interaction with the dark volatility, remains hidden. Always with this approach, we also describe two important phenomena called the clustering and the panic. And furthermore, we show, for example, that in our work, that in the situation called the rich flat scenario, that is the market in the equilibrium, the dark volatility within certain limits does not influence the state of market equilibrium. Okay, another important application from a geometric and topological point of view concern the cosmology. It is in fact possible to use the Pndp approach to interpret concepts such as a space-time, wormhole, black hole, dark matter, quantum fluctuation, strings, etc., even in the point-like version. This study is also the result of a collaboration with Professor Richard Pincock, Professor Said Jafari, and Professor Janab Uzal. For example, we are studying the M theory, in which the Pndp manifold is considered as an emergent space topologically equivalent to a string. That is, we introduce the innovative concept of string as a result of the interaction between dimensions of space-time, one positive dimension and one which we mathematically define as virtual negative dimension. And this interaction make the emerging object unstable, that is vibrating or floating. Okay, this representation, the resulting string as emerging space. Here, the representation of interaction between dimension, our positive dimension of our B manifold, base manifold, with the negative dimension of our manifold. And here is represented 2 subtracted 1 Pndp manifold. From the interaction between the positive and virtual negative dimension, a line interval emerges, topologically equivalent to a string. This approach also modifies the way in which strings can vibrate, because it is necessary to consider the influence that the interacting dimension exert. For example, by altering the structure of the Calabi-Yau manifold. So, string emerging from the interaction or also energy exchange between dimensions can also be considered as a fragment of energy. Okay, in conclusion, we have therefore introduced and shown the Pndp manifold. That is a special type of Einstein-warped product manifold, which, for example, from a pure differential geometric point of view, could contribute to the study of some possible condition for which an Einstein manifold is a submanifold of the base manifold of a possible Einstein-warped product manifold with the same non-positive lambda constant. And from a speculative point of view, we can say that the interpretation of a Pndp manifold can introduce the concept of emerging spaces. And this perspective has, in our opinion, a great potential for application in various sectors. Here, a representation of a Pndp manifold. Here we see a representation of what we said, and we see how a Pndp manifold is structured, and also the speculative interpretation of virtual dimension. Okay, I'm late, so okay, essential references, and I finish it. If anyone wanted to deepen the topic covered, I suggest to learn more about the Warper product manifold, to read the semi-Riemannian geometry with application to relativity, Barrett O'Neill, written by Barrett O'Neill. To learn more about Pndp manifold, I suggest on Pndp manifold, the paper written by me in collaboration with Professor Jenab Ozel, Patrick Linker, and Said Jafari. To learn more about the derived geometry and the Kuranishi neighborhood, I suggest Kuranishi's and the symplectic geometry by Professor Dominic Joyce. And to learn more about negative dimensional space, I suggest negative dimension in general and asymptotic topology, and the negative dimension and E7 symmetry. And to learn more about the suspension, I suggest imaging negative dimensional space and spectra and the string root algebra. Okay, thank you so much for attention, and I apologize if I felt too much. I hope I was not too boring, and anyone interested can write to me at the email address shown here, and ask me all the questions they want. I will be very, very, very happy to answer you in detail. Thank you very much again. Everybody, organizer and participant, thank you very much, and say again if I too much. Thank you.
Thank you, sir. Thank you for your worthy demonstration.
Thank you very much.
To improve the golden moment of opportunity and catch the goal that is in our reach is the great art of life. A very good evening to one all. On behalf of PG and Research Department of Mathematics, we are delighted to offer a gracious welcome to all of you for this valedictory ceremony of 4th International Conference on Current Scenario in Pure and Applied Mathematics 2021. We have been listening to many eminent speakers around the world for 2 days, deliberating in areas of pure and applied mathematics. We hope all these valuable insights gave everyone a new perspective that one should adopt while proceeding their research.
The light of God surrounds us. The love of God enfolds us. The power of God protects us. The presence of God watches over us. Wherever we are, God is. Let us begin this valedictory function with prayer song. Now, I request our students, Ms. Deepika and Ms. Shamali, to grace this occasion with a prayer song.
Shri Lalitambikai Bhuvaneshwari Agama Veda Kalamani Sri Lalita
Thank you, friends.
Coming together is a beginning. Keeping together is progress. Working together is success. I feel pleasure in inviting Dr. D. Vijay Lakshmi, Assistant Professor, PG and Research Department of Mathematics, Konganadu Anthem College, to welcome all.
Thank you. A small cheer and a great welcome makes a merry feast. A very good evening to one and all present here. On behalf of PG and Research Department of Mathematics, I'm very much honored to welcome the August gathering for the valedictory function of ICCSPAM 2021. First, I would like to express my cordial welcome with a fragrance of flowers to our beloved and respected Secretary Madam, Dr. C.A. Vasugi Madam, who is the inspiring force to our department for all our success. Welcome you, Madam. I like to welcome most respected Principal of our college, Dr. M. Lakshminasamy Sir, who is the great personality behind all our success. Welcome you, sir. I like to render my happiness in welcoming Dr. V. Chinnasamy Sir, Chief Executive Officer of a college, for his support, motivation, and encouragement. Welcome you, sir. I welcome our most respected Dean, Dr. S. Palsamy Sir, and Dean Academics, Dr. S.R. Madan Shankar Sir, for support and encouragement. Hearty welcome you, sir. I would like to welcome our most respected chief guest of this valedictory function, Professor V. Lokesha, Department of Studies in Mathematics, Vijayanagara Sri Krishnadevaraya University, Bellary, who is going to deliver the valedictory address for today's function. A teacher takes a hand, opens a mind, and enters a heart. Yes, our Department of Mathematics is blessed with such great teachers. I extend my hearty welcome to all my teachers and our former head of the department, Dr. S.C. Palanisamy Sir, for their blessings and encouragement for the constant conduct of ICCSPAM with great success. I welcome you, sir. All our dreams can come true if we have the courage to pursue them. I welcome all the resource persons, Professor Ismail Nasi Gangul, Professor Dafiq, Professor Ayman Badawi, Dr. Rahul Falcon, Professor Nisar, Professor Said Jafari Sir, Professor Oliver Birjadi, and Professor Alexander for making this ICCSPAM 2021 a grand success. I welcome you all. Also, I welcome all the chairpersons of the various paper presentation sessions. I would like to welcome our department HOD, Dr. V. Gokilavani, and the organizing secretaries of ICCSPAM 2021, and all my department colleagues and students for the valedictory function of ICCSPAM 2021. Once again, I wholeheartedly express the welcome for all for this valedictory function. Thank you.
Thank you, ma'am. There is a saying that the aim of education is the knowledge, not of fact, but of values. May I now invite Dr. M. Lakshminasamy, Principal, Konganadu Arts and Science College, to deliver the presidential address. Sir, please.
Thank you. Most respected Secretary and of Bar University, Dr. C.A. Vagan, the former professors of Maths Department, Dr. S.E. Palchand Sir, Department of Mathematics, both aided and self-finance, faculty members, coordinator Dr. M. Venkatachalam, as Professor of Mathematics, and organizing secretary Dr. E. Prakash, faculty members, research scholars, PG students, UG students, and participants from our college and outside college. On behalf of the management, welcome you all for the valedictory function. And first of all, I congratulate the Maths department. It's a very big department in our campus. I think this is the first department this new year 2021 conducting this international conference. This is the fourth international conference. On behalf of the management, welcome you all, and also I congratulate all the faculty members for your excellent cooperation, and it shows your efficiency. Then coming to the summary of this program, The PG and Research Department of Mathematics, Comunadu Arts and Science College, organized the 4th International Conference on Current Scenario in Pure and Applied Mathematics from 29/1/21 to 31/21 through the Google Meet. Eminent mathematicians from Turkey, Indonesia, United Arab Emirates, Spain, Saudi Arabia, Germany, and Denmark delivered talks in various fields of mathematics. More than 140 participants from abroad and various parts of our country attended the conference and got benefited. 10 parallel sessions were conducted for paper presentation through Google Meet, and 98 papers were presented by the researchers in various fields of mathematics. With this introduction, once again, I'm very happy to participate this wealthy function. I appreciate the organizers, especially Dr. Venkatachalam and Vijayalakshmi Venkatachalam and Prakash for your effort. Once again, thank you. Thank you for the opportunity given to me. Thank you all.
Success. Thank you, sir. Success is the sum of all small efforts repeated day in and day out. Now, let us hear the report of this international conference. For that, I would like to invite Dr. M. Venkatachalam, Assistant Professor, PG and Research Department of Mathematics, Convergence Arts and Science College. Sir, please.
Most respected Secretary and Director, Dr. C.A. Vasiki Madam, respected Principal, Dr. M. Lakshmanasamy Sir, respected Head of the Department, Dr. V. Kogilavani Madam, and today is our Chief Guest for our valedictory function, Dr. V. Logesa Sir, and other faculty members, research scholars, and my dear students. A very good evening to one and all present here. It is my honor to present the report of the conference. The PG and Research Department of Mathematics, Convergence Arts and Science College, organized the 4th International Conference on Current Scenario in Pure and Applied Mathematics, ICCSPAM 2021, from 29/1/2021 to 30/1/2021 in the college premises. The inaugural function of the conference was held yesterday, 29 January 2021, at 10 a.m. through Google Meet. Dr. V. Kogilavani, Head of the Department of PG and Research Department of Mathematics, Convergence Arts and Science College, also convener of this ICCSPAM 2021, welcomed the gathering. Dr. V. Chinnuswamy, CEO of our college, delivered the presidential address. Dr. S. Palusamy, Dean R&D of the college, has given the inaugural address. Dr. S.R. Madan Sankar, Dean Academics of the college, offered the felicitation. Dr. N. Mohanapriya, Assistant Professor of Mathematics, Organizing Secretary of this international conference, introduced the chief guest. Professor, Buludok University, Turkey, delivered the keynote address. The abstract book of the conference, containing 115 abstracts of the research articles submitted by the participants from various countries like Turkey, Indonesia, Denmark, Spain, Thailand, Malaysia, also various parts of India, has released by Professor Dr. Ismail Nasi Gangul through online. Finally, Dr. L. Vidyarani, Assistant Professor of Mathematics, Organizing Secretary of ICCSPAM 2021, proposed the vote of thanks for the inaugural function of ICCSPAM 2021. Followed by the inaugural session, Professor Dr. Defik, Professor of Mathematics, Puluda University of Jemper, also SIGAN Research Group, Combinatorics, Graph Theory and Network Topology Research Group from University of Jemper, Indonesia, delivered a lecture on the topic on the resolving strong domination number of graphs, a new notion, in the technical session 1. In the technical session 2, Professor Dr. Ayman Radif Badawi, Professor of Mathematics, Department of Mathematics and Statistics, American University of Sharjah, UAE, delivered a lecture on the topic on one observing primary ideals of commutating rings. In the third session, Dr. Raul M. Falcon, Associate Professor of Mathematics, University of Seville, Spain, delivered a lecture on the topic New Advances Concerning Critical Sets Based on Latin Square automatisms. Professor Dr. K. S. Nisar, Professor of Mathematics, Department of Mathematics, College of Arts and Sciences, Prince Satam bin Abdullah University, Saudi Arabia, delivered a lecture on the topic Fractional Order Mathematical Model of Novel Coronavirus Disease, COVID-19 in the Technical Session 4. On the second day of the conference, that is today, from 9:30 a.m. to 11 a.m., paper presentation session was held through Google Meet. There are 10 parallel sessions were conducted, and a separate session-wise link has been provided to all the participants who presented their research articles in the respective fields from various parts of India and foreign countries like Turkey, Thailand, Denmark, Malaysia, Spain, and Italy. Followed by the paper presentation session, the second day of the conference, the technical session 5 was held by Professor Dr. Ismail Nasik Angul, Professor of Mathematics, Uludag University, Turkey. He has delivered a lecture on the topic graphs obtained from sequences. In the technical session 6, Dr. Oliver Virjodi from industry person, from Germany, he has delivered a lecture on the topic applied mathematics, examples from academia and industry. In the afternoon session, Professor Dr. Syed Zabari, Mathematical and Physical Science Foundation, Denmark, delivered a lecture in the technical session 7 on the topic almost delta beta continuous functions. Finally, Dr. Alexander Vikasani, Mathematical and Physical Science from Denmark, and delivered a lecture on the topic on Pndp manifolds in the technical session 8. The best paper award in each session was presented to the notable researchers in this conference. Now, it is my honor to announce the best paper award. We have selected 14 papers for best paper award. The first paper, OT27, Chemical Reaction and Hall Effects on Crystallic Flow of Gas and Fluid through an asymmetric channel and the presence of slip effects. The authors are Asa SK and Sunita. And another paper, GT115, Bichromatic Number of Lexicographic Product of Some Graphs. The authors, Dr. K. Kaliraj and M. Manjula from Graph Theory. And another paper in Graph Theory in the same session by Dr. R. Murali, GT116, on the resolving strong domination number of corona and the Cartesian product of graphs. The authors Elsa and Defik et al. From Indonesia. Dr. R. Murali selected 2 papers since both are same marks. So we have awarded best paper award for 2 papers in this session. And another paper from the session chair, Dr. T. Mahalakshmi. The best paper award goes to OT72, a new approach of multidimensional single-valued neutroscopic set in multi-criteria decision making. The authors SP Priyadarsani and Nirmala Irudayam. The best paper award goes to the session by Dr. M. Parimala. TOP 77, that is from topology, beta generalized connectedness in induced fuzzy topological spaces. Authors Saranya M. and Jayalakshmi A. The best paper award goes to Topology 12, the electro multi-criteria technique formulated on bipolar induced fuzzy sets. The authors Ludi Jansis Jennifer and M. Helen. The session chair, Dr. M. Anandi. The best, we have selected 2 papers by the session chair, Dr. K. Kaliraj. The first one is GT15 on equitable coloring of extended corona of some graphs. The authors M. Bharani, M. Venkadachalam and K. Rajalakshmi. The another paper from the same session by Dr. K. Kaliraj, GT26, degree distance based topological indices of some graph transforms. The authors Shobha V. Patel, Meenal and Salja. The best paper by the Dr. R. Bhuvaneswari in the top in the others category, that is OT36, a classification of paraspace forms. The author from Turkey, Inan Unal. The best paper award by Dr. V. Radhamani from others category, OT109, Coriolis effect on ferroconvocation with gravity modulation. Authors S. Marudha Manikandan, Nisha Mary Thomas, and Soya Matthew. The best award, paper award by Dr. M.M. Akbar Ali, GT 116, the vertex irregular reflexive labeling on Jahangir and web graphs by Ika and Defik et al. From Indonesia. The best paper award by Dr. M. Arokya Dasan, Topology, TOP 67, Tikhonov theorem via nano-ideals and micro-ideal topological spaces. The authors G. Jinsey and Dr. C. Janaki. There are two best papers by the session by Dr. V. Vijay Kumar, one paper from differential equation and another one paper from graph theory. In the differential equation, the best paper award goes to D07, Oscillations and Asymptotic Stability of Entire Solutions of Linear Delay Differential Equations. The authors S. Rajeswari, Seba, and another is Seba. And the same session by Dr. V. Vijay Kumar, the best paper selected for graph theory. The paper is GT 101. The title of the paper is Road Accident Risk Prediction with Road Accident Network Graph using graph coloring. The authors Gracelyn S. and Gapsi. And we have selected 14 papers for the best paper award. We will send you the certificate for this best paper award along with the presentation certificate through courier in the week. And this international conference on current scenario in Theorem and applied mathematics helped more than 200 participants from various parts of India and abroad to upgrade their knowledge in the fields of pure and applied mathematics, and it helped our scholars to understand few more such techniques. Thank you, one and all.
Thank you, sir, for reminding about the past 2 days. Congratulations for the authors whose paper has been selected as the best papers. Nothing great will be achieved without a great men, and men are only great if they are determined to do so. May I now invite Dr. N. Mohanapriya, Assistant Professor, Department of Mathematics, Kongnad Arts and Science College, to introduce the speaker, Dr. V. Lokesha. Ma'am, please.
A very good evening to one and all. It's my great privilege to introduce our distinguished chief guest, Dr. V. Logesha, Chairman, Department of Studies in Mathematics and Computer Science, VSK University, Bellary. He completed his PhD from University of Mysore. His area of research include functional analysis, graph theory, operator theory, and mathematical inequalities. He received Doctor in Science degree from Berhampur University. He has more than 25 years of experience in teaching. He has published more than 150 papers in well-reputed journals. He is the chief editor of the journals, Journal of Analysis, Journal of Scientific and Industrial Research, and Journal of Intelligent System Research. He is an executive editor in Bulletin of Baranam's Mathematical Society. He is also an editorial member of Ultra Scientist for Physical Science, International Journal of Computer Science and Engineering, and Information Technology. He is an advisory board member of Asian School of Management and Technology, International Journal of Mathematical Sciences and Engineering Application. He is Board of Studies member of VSK University, Bellary, JSS College, University of Mysore. He is reviewer in many journals like Zentrablatt Math Journal, American Mathematical Reviews, Nonlinear Analysis Theory, Methods and Applications, Journal of Computer Science and Mathematics, Applied Mathematical Letters, and many more. He is a life member of IMS, ISTE, JMS, Ramanujan Mathematical Society, and IASR. He has been awarded MDPCSL Cash Prize in 1993 and 2003. Outstanding Intellectuals of 21st Century 2010, Great Britain. We are grateful for his esteemed presence and among us today. I wholeheartedly welcome Dr. V. Logesha to this valedictory function. Thank you.
Thank you, ma'am. Good evening to all of you. Ladies and gentlemen, colleagues, my dear friends. It is an immense privilege to be a guest in this valedictory function for this vital conference, and it is a great to see the re-emergence of interest in mathematics on the part of distinguished professionals. I would like to thank all the presenters and participants and also best paper awardees who have joined this conference from all over the world in this pandemic situation. I believe that during these 2 days, all of us have obtained fruitful discussions and deliberations. I have believed many researchers had good experience and good lessons learned. Many people have observed that an assortment of good work has been done in the area of mathematics and its allied areas. In this 4th international conference, the main theme is current scenario in pure and applied mathematics. We have learned a lot from the keynote speakers, the veil of a new era of mathematics. Let me begin by thanking to my friend Dr. Venkatachala. He has taken a hardship for your stewardship of this conference. And for the excellent summary you have just provided, it tells how you done the conference. I congratulate you and your team. This will be helping to plan what we need to do next, both here in the Kongu Nadu Institute. I have a long association with the Kongu Nadu Institute and our colleagues. We should appreciate for their great effort towards the success of the conference. Because of the time limitation, I cannot mention all the names here, but we will not forget their hard works and great contributions. I have involved many events organized by PG Department of Mathematics of Kongu Nadu, especially the Motivational Director, Dr. C.A. Vasiki Madam, Inspirational Principal, Dr. M. Lakshminaswamy, meticulous efforts of the conference by Dr. V. Kokilavani, convener, and administrative faculty and technical team are all well cooperative, engaged in hard work and dedication. On this point, I congratulate scientific committee members and organizing committee members for their active programs who can share their up-to-the-date experience and facilities. Finally, I would like to thank Kongu Nadu staff for organizing this wonderful event and ensuring it ran so smoothly in this pandemic situation. Furthermore, you have participated actively in online mode. I am sure you are all looking forward to offline mode in the next coming conference. I heard that almost 121 papers came and 14 parallel sessions are done. I am very much thankful to the organizers because they also given 14 best paper award. That is one of the encouraging thing for the young research scholars. Thank you for the organizers. And also I thank you once again for your participation. Thank you for giving me an opportunity to say few words. Jai Hind. Thank you.
Like the rainwater bringing life and prosperity to the land, your words bring enthusiasm and strength in our hearts. You ignited our soul. Thank you so much, sir.
Thank you, ma'am.
Thank you, sir. Expecting the participants to give feedback about our international conference. Participants, please. We are expecting the participants to give a feedback about our international conference. Participants, please. Shivanand, sir, please proceed.
Yes, madam. Ma'am, can you hear me, madam?
Yes, sir. Yes, sir.
Good evening, everyone. It is an excellent. All the sessions are very interesting, madam, and at the same time, very good organizers. Actually, I have submitted last only, even though they have accepted my paper and they have given me an opportunity. It is I thank for the organizers for accepting me and giving me an opportunity to present. And as I am a research scholar, it is much helpful for my research work. Thank you, madam. Thank you, everyone. Thank you, madam.
Thank you, sir. Any other participants? Please do proceed.
Hello, myself Shobha Patil.
Yes, ma'am, you are audible.
Yeah, I am very much thankful to all the organizers. It was the conference was well organized, and conducting the different parallel sessions was very difficult, at least for the online mode. The organizers have done very good work to have the session smoothly, and because of the short of time, I didn't get personally much time, but it was very good session, and all the papers were very nice. Well done, organizers. Thank you.
Thank you for the valuable feedback. Gratitude can transform common days into thanksgiving, turns routine job into joy, and change ordinary opportunities into blessings. Now I request Dr. E. Prakash Sir, Assistant Professor, PG and Research Department of Mathematics, Konganadu Arts and College, to deliver the vote of thanks. Please, sir.
Thank you. The essence of all beauty art is gratitude. I am Dr. E. Prakash, Assistant Professor of Mathematics, deem it a great honor to propose the vote of thanks to all who have helped us in making this conference such a resounding success. First, I would like to thank our President, Dr. M. Arichami sir, beloved Secretary Director, Vasudev ma'am, for giving the opportunity to organize this international conference on current scenario in pure and applied mathematics. I thank Principal Dr. M. Sir, Dean Academics, Dean R&D, and CEO sir for their support and guidance and their presence in the conference. I thank all our research persons from various countries for sharing their findings and knowledge with us during this conference. I thank all the resource persons who have acted as the chairperson of the paper presentation session. I would like to thank Dr. V. Lokeshar for his delightful valedictory address. Thank you, sir. I would like to thank the convener, Dr. V. Kogilavani ma'am, head of the department, and coordinator, Dr. V. Venkatachalam, for this conference, for taking effort in organizing such a wonderful conference. It is my duty to thank the organizing secretaries, Dr. L. Vidyaran and Dr. N. Mohanapriya ma'am, and all our faculty members, Dr. D. Vichalakshmi ma'am, M. Vigneshwaran sir, Ravichandran, Priyalada ma'am, Vivek Prabhu sir, Sadish Mohan, sir, for their effort in bringing this conference into reality. I would like to express my sincere thanks to our MPhil and PhD research scholars and students for their support during this conference. Finally, I thank all the people who have participated overwhelmingly and making this event a great success. Thank you once again. Thank you.
Thank you, sir. It is on occasions like this we get opportunities to test. It is on occasions like this we get opportunities to understanding. We look forward to get an exposure about what the best of the minds thinks about. That concludes a remarkable, memorable, and knowledgeable event. We promise you all that in the next year, we'll enter into the field with some more innovative ideas to nourish everyone's mind. Thank you, everyone. Now let's stand for National Anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मागे गाहे तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे